go be there. So they were being
Yeah.
recorded, Leonard. We'll have to stop telling jokes. So,
Well, that'll
I
be a
mean,
little
except for the
hard.
one. So, I'm an emeritus and you're in the dean's office now, so we can tell this joke, what a professor is.
I
Heard
don't
of
know
it?
what a professor is.
It's somebody who talks in other people's sleep.
Okay, so
I have one last chance to talk in other people's sleep. I never
that's
dreamed.
true. I should probably turn off my video when you get to your slides.
Yeah, well, yeah. Hopefully I won't fall asleep. That's what I'm hoping. So, but
Yeah,
I
so
did well. So okay, we got about 4 minutes till 6. It looks like I'll just mention. I think they are going to teach. I think Sue and Kim. I'm not sure who's running the other stuff. Are going to keep the chat open and or yeah,
the
I think
question and
it's
answers.
yeah.
So
So I don't know that I'll be able to try and answer those to go along, but I'll try and field as many as I can when we're done. Is that kind of how this normally works, Leonard?
yeah, I'll keep an eye on them, and if there's
Okay.
something worth interrupting you for, I will. But
Okay. All right.
otherwise, I'll keep track of the good ones to ask you at the end. If I'll see how much time we have. Hopefully, we'll get through them all, but we may not.
Yeah. 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 Depends on how many people fall asleep. So
Yeah.
also near the end, there is a YouTube about the Paulding lights that the student chapter of the SPAE made many years ago. I helped stand that up, and I was the first faculty advisor for that. So SPIE stands for the Society of Photo Optical Instrumentation Engineers, but nobody can remember that. So hey Leonard,
Mm-hmm.
did you know that if you blow across your brandy, everybody will think your tea is really hot?
That's true. That's true. But it's hard to blow across that because I've got a top on it. So
What
that,
keeps your brandy at just the right temperature? Then is what you're saying.
well, no, it's uh, when I tip it over, it doesn't spill nearly as much.
There you go. All right.
So
So anyway, so anyway, I used to give the students in SPAE a project every year, but the very first year, I asked them to go down and see if they could figure out what was really going on with the Paulding lights. And so there's a YouTube in there that's almost 5 minutes long. So we'll play a couple minutes, but I think Sue said so the link to the YouTube, if you want to watch the whole thing, is embedded in my talk. But I think Sue is going to paste that into the chat at some point also. So if you feel like watching that, you can find it. But if you also just type into the YouTube search something like MTU Paulding lights, it'll pop up. And then also if you watch I think it is called The World's Strangest Weather on the Weather Channel. This is a completely different video about the Paulding lights, but I actually participated in it from went down there and showed the people from the Weather Channel around and did a little interview down there. So
well, if it has you on it, I mean, I'm sure it's strange weather.
yeah. Well, so I did tell them, and I was a little disappointed they didn't use this. I can't remember exactly what I was going to say, but I had, told my wife about, I was going to do this. And I actually practiced it in my head and then in front of the mirror a couple times so I could say it with a straight face. But they actually recorded me saying that something about the fact that, well, we know that these lights are, at least some of them are caused by a temperature inversion in headlights on the highway and all that stuff. I said, but we've never been able to disprove the existence of a ghost. So they didn't use that. So but
All right.
but anyway, it's a nice clip. So all right, well, looks
It
like we
looks
got
like
about
it's time to start. So let me do a brief introduction here and welcome everyone to Husky Bites. As Mike was saying, Janet is off being inducted as a fellow of the American Ceramic Society. So she left a poor substitute as host. So you'll have to suffer through the evening with me. Um, let you know what our menu is for this fall. We are on the 10th, which we have Mike Roggemann, a colleague of mine from electrical and computer engineering. I've known Mike for, well, ever since he's been at Michigan Tech about 25 years ago. If you're interested in the uh, ones that we've done previously, you can find those on our uh, go look at Husky Bytes at our website, and you can get links there. And next week coming up, we've got sensing smells, so we can find out something about how we smell by Yixin Liu from chemical engineering. So with that, I'll turn it over to Mike and I'll see what he has to say. I can stop that
Okay.
share.
Thanks, Leonard. So, are my slides up on the screen now, or do I have to reshare them?
You need to reshare them.
Okay, I will do so. All right, are we good?
We've got you.
Okay, I'm going to see if I can reduce you to the taskbar thing. There we go. All right. Well, hey everybody, welcome. I have no idea how many of my former students are out there, but a special welcome to all of you. If you remember me from your Michigan Tech days, why I would welcome the chance to hear from you that I'm an emeritus professor now, and my mtu.edu address will probably outlive me at this point. So just drop a note if you get a chance and let me know how your career's been going. All right, so here's an overview of the presentation. And as I mentioned earlier, I don't think there are any clear few, graphs, but no equations at all. So if you're a student of mine, former student of mine, you'd be just as shocked as I was, when I got into this and realized there are no equations. But that's what this is. So we're going to talk about where turbulence comes from. How does it affect optical systems, which have to work in the presence of the atmosphere? A little bit about what kind of technology is available to correct these effects, and then about some strange ones that you may or may have not seen. One of the effects is called fatamorgana, and the other one is the Paulding lights, and then we'll wrap things up. All right, so where does turbulence come from? Well, it's pervasive, and pretty much every visible and infrared optical system is affected to some extent by turbulence. Now, what is turbulence? Well, here's kind of the top level layperson's example of how it works. The energy pump is the sun. It has the effect of warming the ground. The ground warms the air. Air is naturally becomes buoyant with increasing temperature, and it has low kinematic viscosity, which means that it mixes very well or very easily with itself, and this causes some interesting phenomena then that we'll see here. Now, the sun heating the ground, of course, causes large structures of warm air to start rising, and then this low viscosity thing causes these big airflows to break down into ever smaller structures. And the term of art for these structures is called the turbulent eddies. Now, I have had students over the years who were also musicians because, of course, lots of Michigan Tech students are multi-talented. And I had mentioned over and over that I thought the turbulent eddies be a great name for a band. And then the day came finally where I had a student who was somehow aware that there is, in fact, an Irish band named Turbulent Eddie, who has some YouTubes, by the way, because I've listened to them. And but this is apparently a reference to whoever Eddie is. It has poor luck with relationships. It's not a reference to atmospheric physics. So, but anyway, yeah. So, yeah, Eddie is apparently not a gifted relationships person, but he's a good musician, and I would encourage, if you like that kind of thing, it's kind of Irish, obviously, but you can listen to it on YouTube if you'd like. Turbulent eddies are everywhere. So a little poem here. Big worlds have little worlds, which feed on their velocity. and little worlds have lesser worlds, and so on to viscosity. So it's the only poem I like. There are a couple of limericks I like too, but we're not going to repeat those here because they're a little colorful for a general audience. But anyway, so it looks like this. So I don't know if you can you see my arrow moving around here, Leonard, that from my
No,
mouse?
not really.
Okay, well, in the plot on the left, the what that's trying to conjure up is this idea that these big structures caused by heating the soil just break down ever smaller structures, but the distribution of those structures is actually governed by a power law. And in fact, if you were to look in the literature, you would look up like energy cascade or Kolmogorov's power law. Will get you to this in a much deeper discussion of this effect. Now, on the left, you can see something of this mixing. This is a jet, and the flow is visualized by a technique called laser-induced fluorescence. But you can see the effect of these little whirls are, the big structures are just breaking down into smaller structures constantly. And it turns out that Kolmogorov showed that that is in fact all they can do. And but the effect on optical waves is profound in many cases. All right, so here is a simple visualization of how this works. And they were asking me earlier about, getting some videos of this. And I said, well, I was stationed in New Mexico when I was in the service. And you see this all the time, like you're driving down the highway and the highway is very, very hot. And cars coming at you, right? And so this air is rising up off the pavement, this turbulent mixing is going on. And so instead of seeing like a very crisp, clear outline of a car, you see the thing on the right, which is this car is fuzzy, the edges are deformed, and it's changing constantly because, of course, the air is just in constant motion. So this is just a simple example of how turbulence affects a simple imaging system, which is just the human eye. All right, so
And one of the things to point out is we've got a lot of links in the chat. One for some music by Turbulent Eddie and other things. So, but go on with your poll.
Okay, so here's a poll question, and everybody can read that.
So it looks like we've got a group here that has not fallen asleep yet.
Yeah.
But you still have time.
Yeah. Here we go. So there's a vote for the aliens. I was hoping somebody would, root for the aliens, but I would say 89 out of 110 people got it. Got it right. Heating by the sun. And I just made up the rest of that stuff. So, all right. So let's go. Can we go forward? And can I don't know if I can remove the question. Just right in front
Yeah,
of
you can
go.
just close the window.
Close the window. Okay. There we go. All right. So let me see. Oh, there we go. Okay, so we're in the right spot. All right, very good. So turbulent eddies, cause the turbulent eddies cause a mix of randomly sized and shaped pockets of air. Now, the thing is, these little pockets of air, which are randomly sized and shaped, are defined by having a fairly uniform temperature, but they're also constantly mixing. Now, it turns out the other bit of physics is that the index of refraction of air is quite sensitive to temperature. And because of that, well, that's where the trouble starts, right? There is now a non-uniform index of refraction between you and whatever you're looking at or whatever you're trying to fire a laser at, and that bends the light. Now you can see in the lower right here, there's a little figure that shows the deterministic effect of refraction by a piece of glass. But just imagine this going on everywhere in the atmosphere randomly all the time. And that's the nature of atmospheric turbulence effects on imaging and laser beam projection systems. Now you can see this on astronomy. So this is back in, I guess, a long time ago in 1996. My colleague and good friend Byron Welsh and I wrote a book on this stuff. And you can, this is on the left here, then are some images drawn from the book. So on the bottom left is what an imaging system would do if it were working in a vacuum and it were perfect. And the term of art in optics for a perfect imaging system is diffraction limited. And diffraction is just the term of art for the effect that arises from the fact that the edges of a lens act like a cookie cutter on a propagating field. And nature hates sharp edges. And so what it does is it makes the response kind of ring. And in the lower left, you can see those rings are called the airy disk. Now, the brightness of the airy disk is a little bit exaggerated there because when I displayed that, I actually took the log of the intensity to kind of compress dynamic range. Normally, you would see the central core and a little hint of the first ring and none of the others just because they're so dim. Now, if you look at a star and for a long time, then the middle image is an example of what you would see, right? And so the fact that that is just much, much broader than the diffraction limited image is an indication of the difficulties associated with imaging through turbulence. And in fact, that middle image is pretty much the motivation, or much of the motivation for space telescopes, believe it or not, is to get above the atmosphere so that you can get close to that bottom left response to images of stars. That and the fact that stuff astronomers are really interested in is so heavily redshifted that you might not even be able to see some of it through the atmosphere. So, but and then the top left is an interesting thing also. This is what you would see if you took a very short exposure of a star through atmospheric turbulence. You can see that little intensity distribution. That's actually those are called speckles, and that's an example of speckled image, which indicates to an optical scientist, by the way, that for example, in the middle image, you can look at that if you've got an electrical engineering background and say, oh, wow, the high frequency content of that is just gone. It's been lost by, averaging over a long time. When you look at that image at the upper left, you would say, ooh, there's high frequency information there, but it's been randomized, but maybe we can use that. And it turns out you can use that, but then you have to use equations, and I promise not to do that. So, but if you want to look at the equations, just buy a copy of Imaging Through Turbulence and say, well, I wouldn't even say it's in print. The technology that CRC has now is basically if you order the book, they will print you one and like ship it the same day. So somehow they can do that. They don't have a warehouse full of imaging through turbulence. Let me tell you, it's
yeah. So is that top image an actual photo?
No, that's a simulation. But I've taken a great many photos that look exactly like the top one, the middle one. That's for sure.
Okay.
That is a very, very good rendition of what you'd see if you even went out to the observatory by Atlantic Mind and to start taking short exposure images. They would look like that.
Also, so the university has a observatory out at Atlantic Mine.
Yeah, it's outside Atlantic Mine, but you should talk if anybody's interested in that. Professor Middlebrook is kind of the owner isn't the right concept, but he's the faculty member that's kind of responsible for well, I mean, it's a shared resource, but like he's a coordinator for it. I'm not sure what the right term is, but he's the guy to talk to if you want to go see it or look at it. There at least used to be a really nice telescope, and I actually bought a new mount at some point when I was on the faculty, and So it's a good system, but the problem is, the observatory goes for what like a project comes along and it's just used intensely for a few months, and then it sits for a couple of years, and then it's
Yeah.
used intensely again. So it's got to be cleaned up and kind of brought back to life every time there's a long pause. But I saw
Yeah,
it at
yeah.
the
There's a website in the chat about the Amjoc Observatory. So
yeah, yeah. But there's some cool stuff. Professor Nemiroff from physics had a concam out there for a while, I think. So if you look up the MTU concam, you'll see that that's like a hemispherical imager. So that was pretty cool. And then they were also, I don't know if they ever put it out there, they also had some magnets to attract particles that were from comets that had burned up in the atmosphere, which I thought was pretty cool also. So I'm not sure they ever put that one out there. I mean, he asked me about it. I'm like, yeah, let's put that out there. Let's see what we got, but I never heard how that came out, or even if it actually happened. So,
yeah.
but, all right. So, what happens when you try to shoot a laser through this stuff? First reasonable question is, well, why would you want to shoot lasers? Well, optical communications, for good reason. In fact, optical comm is a great way for what like people who do internet communications and stuff like that would call the last mile, right? If there's some place that is so rocky or so inaccessible that you have to, find two spots to have a clear line of sight and set up a free space optical system, you can do that. And you say, well, that's nuts. Where could you not run a wire? And I'm like, well, if you ever looked at the terrain around the volcano called Mauna Loa in Hawaii, that's a fine example of a place where where they've got an optical comm link, and there are all kinds of places like that where it's either unreasonable or impossible to run a link. There's also optical comm, I believe, to space for some commercial applications. I know, like after the World Trade Centers were attacked, when those buildings fell into the street, they actually crushed a fair amount of the infrastructure which is running in the channels underneath the street for internet communications for the traders, and they restored a good chunk of that very quickly with free space optical links running between the buildings, for example. There's all kinds of remote sensing for just like measuring the range, or if you're into self-driving cars, you might want to measure point clouds or do 3D imaging as part of that. Also, another aspect of 3D imaging is like 3D surveying, which is very important for all kinds of civil engineering stuff, spectroscopy. Like if you've looked at the Mars rovers, they actually have a laser strong enough to do spectroscopy, where you have to basically shoot your sample with enough energy to basically vaporize it and then look at the spectrum of what's in the vapor. So and then there's always research, and a lot of this has been in the news, to shoot down drones, mortars, missiles, etc. As defense applications for the stuff to help keep our soldiers a little bit safer. So what does the atmosphere do to the laser beams? Well, makes them jitter randomly. Okay. In fact, it makes them jitter so much that sometimes a device in the transmitter called a fast steering mirror, coupled with a tracking system and a control law, is required to pre-compensate for this effect. So basically, you have to have a way to measure the tilt and then conjugate that with the outgoing beam. So if the beam path is long enough, the laser beam can break up into speckles also. And that's a huge problem for laser comm systems, because now that speckle pattern that you saw on that slide is sweeping back and forth across the receiver aperture, and the power intercepted by that receiver is then fluctuating wildly. And then that in turn can affect the bit error rate of that link. And everybody knows, well, I can't say everybody knows, but it's not, even if you don't know this in your bones, it's easy to believe that the lower the bit error rate, the better the comlink, and that is absolutely true. All right, so here's a visualization of that. And so this, you can see the transmitter propagating through the turbulence, the distorted wavefront. And this is, let's see, so I think this is real data from the Canary Islands, but this was published in a Nature article, and the link is down there at the bottom, so you can go look at it if you want. But if you look at on the lower right where it says frame 1, frame 2, frame N, this is a camera that actually was designed to measure those speckle patterns in the pupil of the telescope. So this is pretty interesting stuff, right? You can see direct visualization of that phenomenon that I was showing earlier for an imaging system that happens. So a slightly different manifestation that it also impacts laser systems.
On those that frame rate, what how quickly are each of those images being taken?
Well, it depends on basically the wind speed and how turbulent the air is, even without the wind. But 1 to 10 milliseconds kind of correlation length is pretty. It was within the range of lots and lots of experimental observations.
Okay.
Okay, here's poll question 2. What is the physical process that best describes how turbulence affects light?
Well, it's clear that you haven't been putting them to sleep yet. Those of you who were not here at the beginning, Mike told a joke about what is a professor. Something about they get to talk and put people to sleep. So
no, I said it's somebody who talks and other people sleep. That's what I said.
All right.
But that's what a professor is. But everybody's awake. This is shocking. I've never had this many people stay awake in one of my classes. Oh, wait, there's 151 people participating, but only 112 of them answered. So I think there's a good chance 39 people are asleep, Leonard.
All right.
Which is about right. Which is about right, actually, for that would be pretty standard for me.
Okay.
All right.
So did they get it right?
Yeah, I'm not sure what disambiguation is. I thought I was making it up, but maybe that's a thing. But the correct answer is D, refraction, and most of you got that. So, all right. So I'm gonna click the X here and proceed. Oops, there we go. All right. What did I do? I pushed it twice. Okay, so what to do? Well, one way to overcome this is with adaptive optics. And adaptive optics are pretty cool stuff. Basically, you have a deformable mirror on the left there in the middle of the left side. You can see now this mirror is trying to mechanically undo the effects of turbulence by constantly changing its shape to kind of conjugate the air rising from the atmosphere. Now, you would say, well, how does it do that? Well, a deformable mirror is basically a thin reflective face shield glass. On the back of that, then there are a bunch of electrically controlled actuators that have maybe a full stroke of 3 or 4 microns, but that's all it takes. And so by pulling and pushing on those actuators, you can change the shape of that thin face sheet of glass to undo the effects of turbulence. And you say, well, how do you know what shape to do that? Well, there's a Hartmann sensor, which measures the wavefront in a complicated way that requires equations, which you may recall I said I was going to do. And then there's a control system that drives that. And so basically, then the science camera is always seeing the corrected wavefront.
So how quickly does this have to work?
Well, it has to, the closed loop bandwidth has to be faster than the correlation time to atmosphere. So basically, if you have like 10 millisecond correlation time, that would correspond to 100 hertz. But, a rule of thumb is that basically you need to sample, 8 to 10 times faster than that. So the Hartman sensor would then be running at like 800 to 1,000 hertz. So that's kind of, now if you put this on top of a tall mountain, which, is an obvious thing to do, then you can get that down. But really, the slowest one I've ever heard of runs at maybe 200 or 300 hertz. That's about as slow as it can go at the best observatory.
Okay, and they have to move these mirrors by portions of a wavelength.
Yeah, they're typically for visible and near infrared, it would be hundreds of nanometers to maybe a little more than a micron or two. For deep infrared stuff, it would be a little bit longer than that, right? Because like thermal infrared would be between maybe 8 to 14 microns, and so you'd have to have maybe 4 microns. But truthfully, you'd never. Well, you'd see some, like if you're looking at the thermal mirror, you would see some minor changes in like what the reflection coming off it is, but you couldn't actually see the mirror move. That's
Okay.
not enough motion, and it's happening too fast for your eyes. So, but here's an example of what adaptive optics could do. So on the right, like when Neptune was discovered, that was the best image of Neptune that could have been had. But with adaptive optics, you can get the image on the left. And so this is just an example of the power of this technique. And I should mention that this has all come about really in the past like 30 years. It went from nothing but the image on the right to routinely being able to get the image on the left. And so that's incredible, because this stuff is pretty fantastically expensive also. but the best observatories all have it. Well, I can't say all. I don't know if they all have it, but they either have it or they want it very badly. And that's the nature of this field. All right, so now bear in mind that from the Earth, Neptune subtends a very, very small angle. There's another set of effects that arise from looking at objects with a big angular extent. And so you can see different parts of this image. Now the ship is actually moving back and forth, but this looks like a Coast Guard cutter to me. Those 45 footers like they have here. But you can see, right, that this is shimmering in addition to the boat moving back and forth. And this is because light from different points on that ship pass through different parts of the atmosphere, and they pick up different errors. And this is, again, a very, very hard thing then to compensate for in the real world. This takes a whole different set of specialized algorithms and stuff like that. But this effect is what I would offer up as the collegiate word of the day for today, which is anisoplanetism. And anisoplanetic images can only be partially corrected with adaptive optics, and a great deal of additional image processing is required to go beyond that. But once again, our group at Michigan Tech had worked in that field plenty.
How far away was that boat?
Well, it was probably a few hundred meters, but with a really good lens, is my guess, like a really big lens.
Only 400 meters.
Yeah,
Okay.
that's all it takes if it's hot enough.
Okay.
That's all it takes. So, all right, so here's the effect on a laser beam. So you can see the receiver, little circle there. See this is in super slow motion, but you can see on the bottom there how the power received fluctuates. Now, I suspect this was very close range because the incoming pattern isn't all that badly speckled, but you can see the wind, and it feels like the wind is kind of blowing it across from right to left. And that's because the wind is kind of blowing it across from right to left. So All right. So now, cool stuff here. The last topic is mirages, temperature inversions, and sort of the things that can happen from that. So a normal mirage, which you probably just about everybody has experienced, like if you look at across the desert or across some really hot place, what you'll notice is that the ground looks like it's shimmering. It looks almost like the surface of a pond or a lake. The reason for that is that there's a strong temperature gradient near the ground that is making light that actually started out in the sky refract towards the cooler air. Okay, so this means like for a regular mirage, that light from the sky comes, it interacts with the warm air close to the ground, is actually bent back up. Okay, and then there's turbulence thrown in there too. So the reason they look kind of bluish or bluish white is because it's light that came from the sky and it's refracted back up from the ground, and it appears to shimmer because of the fact there's also turbulence in the mix. So this is what I would call a normal mirage. And if there is a temperature inversion, which can happen in valleys or whatever. So normal kind of meteorological thing is that air is warm near the ground and it cools gradually as you go up, right? Now, if it's cool near the ground, warms up for a bit, and then cools down again as you go up, then that's called a temperature inversion. Okay. And once again, light trapped in there has the effect of being bent towards cooler air. But then that's what gives rise to some pretty cool stuff, like fatamorgana. So this is so fatamorgana. I just borrowed the Wikipedia stuff on this, but it's an Italian term for this effect, right? So there's an optical duct created by an inversion, but the effect on light, for example, emanating from that ship on the bottom, is to make it appear to be floating in the air. Right? I mean, it's really, really something. I mean, somebody actually snapped that picture, and that's just an example of light emanating from the ship being trapped in an optical duct formed by an inversion, and then when it's rearranged, when that light coming in is rearranged by your eye, or any lens for that matter, it looks like the picture on the bottom, right?
What's kind of interesting with that is that picture of the ship floating.
Mm-hmm.
If I'm remembering that right, was shot off the coast of Cornwall, which,
Could be, yeah.
as you know, has a relationship to this area too, with all the Cornish miners and the pasties they brought over.
Pasties, right?
Yeah.
Love pasties. Can I say where my favorite pasty comes from, Leonard, or is that
You
not?
can.
Props in Twin Lakes. There, get that. So
All right.
hopefully they'll send me a case of free pasties now for giving them a little plug. But never drive by crops without stopping. It doesn't matter. If we're going away, we stop and just eat them while we're driving. And if we're coming back, we grab them and have them for dinner. So.
Okay.
All right. Yeah. So okay. So here we go. So this is the other thing. The Paulding lights is also a result of a similar thing.
So Paulding, where is that?
Well, that would be south of here. That is on is it US 45 going south? Like you up
Okay.
here, Bruce. Yeah. So it's
So
easy.
you have to go past Krups.
No, you go the other way.
Oh, okay.
Wait. No, I'm trying to think. You would go by Krups. Yeah. So yeah. You go 45. Yeah, you go through Bruce Crossing. Yeah. I'm sorry I drive through. Well, actually, because of this, I can't stop in Paulding anymore. They, have a little sign with my face on it, cross through it. So but in any event, the Paulding lights are caused by a similar thing. So you can see like this image here is from like the spot where the Paulding lights are observed, which is clearly in kind of a valley. And if you can look, like up along the pole line there, you get a feeling that you're seeing maybe the highway up there, and I actually suspect you are. But what happens, I think, meteorologically, is that certain weather conditions can give rise to the case where cold air actually slides down underneath the warm air that's at the top of this valley and creates an inversion, which then creates a reverse mirage. But it's a reverse mirage of headlights on US 45. And so you've got, light from the headlights. Some of the light from headlights is being bent back down towards the ground. And then there's turbulence in the mix, and it appears to kind of shimmer and bounce around. And this is the video. And I'm not going to play all of this, but Sue said she was going to put this link in the chat so that if you want to grab it and watch the whole thing later, you can do this. So we'll just play.
Are you hearing the sound there, Mike?
I'm hearing. Yeah.
No.
Oh, good gracious. Oh, I'm sorry. I thought everybody could hear that if I played it. So
No.
no, well, doggone it. Well. Anyway, you can see. By the way, you saw the name Jeremy Boss. He was one of my PhD students back in the day, and he's now a faculty member in EC.
And I think that he is an alum of Husky Bites, if I remember correctly.
Oh, that could be. Yeah, that could well be. He has quite a portfolio. I don't know if we can scan ahead here and see there. Let me just. This is.
There's no way to reference. You see a light,
So,
and the light is actually moving.
all right,
If you look
so
at the telescope, you can see the light
there
moving
you
through
go. All
this
right,
state.
we'll pause it here. So, all right. So, oops, I'm trying to pause it. Turns out I'm just not very good at pausing it. Sorry, I thought that would play. So, well, here's poll question 3. So, is there anything optical at the atmosphere actually helps?
All right, we've got 3 questions here, and there's a lot of going back and forth here. Oh, we've got over 100 people have answered so far, and we've got 150 or so.
104 down to 149.
Okay.
Yeah. Well, it looks like the C's have it to me, and that would be my answer too. Is that there's not much optical at the atmosphere helps. It's very useful for breathing and flying airplanes and stuff like that. But in terms of optics, the most interesting thing is it gives rise to some really cool effects, like the pulsing lights. And in fact, I'll tell you, I don't know how long they leave the comments up for videos like the one I just shared with on the pulsing lights, but some of the comments were great. Like somebody said, like, well, ghost hunters were out there and they couldn't, or paranormal something or other was out there and they didn't find anything. So why would we think these guys would know anything? The other thing is I actually got a couple of phone calls because once you understand what's going on, you're right. It's not hard to imagine that any place where there's a valley where cold air can slide underneath the warm air, and there's also a road or some other source of light, you would see this. And I actually got a couple of phone calls from people asking me to, send out a team to look at their weird lights, but I had to explain that there is no team. Just some really good
I don't
students.
know if they were willing to pay the travel expenses. You might be able to
Yeah,
get
yeah, that
a team.
I actually did ask, but nobody, wanted to quite go that far. So there was no team. So, all right, I'm going to try and bring this in for landing and field a few questions, and then everybody can get back to the rest of their evening. So there are some interesting effects, and mostly it's due to the natural tendency of air to become turbulent. In fact, it's almost impossible to keep it from getting turbulent. Um, Huge amount of work has been done to understand the nature of this, but that's all mathematical, and not going to torture anybody in a talk like this, that kind of math. But the understanding of it has allowed means for overcoming these effects to some extent to be developed, and that's where I spent a good chunk of my career working was in mitigating those effects. So, all right, Leonard, that ends the presentation.
All right.
Should we handle some questions or
Sure. If you stop sharing your screen, we've
do
got
that?
one from Larry Aldrich. He was wondering if these same sort of effects of atmospheric turbulence effects relating to 28 gigahertz satellite signaling. So what is the effect of higher frequencies?
Well, so let's see. 28 gigahertz. I'm not 100% sure at that band. There, I can't even remember the plasma frequency of the atmosphere. I think it's lower than that. So yeah, I'm not sure there'd be much of an effect. Maybe if the path length is long enough, but not 100% sure.
Okay.
I'm a terahertz guy, not a gigahertz guy. That's what.
And we had another question about those. If you remember those three images of the speckled image, the long-term image, and the fairy disk.
Yeah,
What type of image does the Webb telescope capture?
the bottom one.
The bottom one?
Yeah, and that's a little more complicated than that because that's a segmented telescope, and when you look at the pictures they're getting, right, you'll see like the response of that to a point source input is a little different. But basically, the goal of the James Webb was to get that bottom one.
Okay. So another question, though, you're talking about the adaptive optics on astronomical observatories, and one person was wondering if the Lowell Observatory in Flagstaff uses adaptive optics.
Ooh, boy, I'd have to check, but I imagine they do. In fact, I was out there, but there are actually a bunch of observatories at the Lowell, and I'll double check here while we're talking here. So I wasn't at the main one. I was out somewhere else, but let's take a look. By the way, Lowell Observatory, not Lowell. Lowell Observatory is in Flagstaff, Arizona.
Right.
Yeah, whereas Lowell, Massachusetts probably doesn't have.
No, at Lowell, Massachusetts would probably be a little cloudy.
Yeah, let's see. I don't know off the top of my head. Like I said, I was there for another purpose. And in fact, I wasn't even exactly at the Lowell. I was at Anderson Mesa for the Navy precision optical interferometers, but I was out there and I didn't think to ask. So I wouldn't be surprised. The Lowell Observatory is famous, by the way. That's where Pluto was discovered.
Right,
So,
right.
yeah.
Another question about mirages. Wondering if polar mirages are just a special case of Fata Morgana, or is it a unique phenomena?
I don't know what a polar mirage is, so I don't know.
Okay.
Yeah.
And I'm not aware of what those are either.
Yeah.
And let's see. What else do we have? How many when we're talking about these deformable mirrors, how many segments are those?
Oh, well, so the face sheet on the front is generally continuous, but there are on the back, the number of actuators goes from a few tens to a few hundred.
Okay.
Is kind of the state, maybe, well, actually several hundred. That's kind of the state of the art. So,
And some of the larger optical observatories do have segmented mirrors. Some of the newer ones,
oh
from my
yeah, absolutely.
understanding.
Yeah, like the 30-meter telescope and
Yeah.
yeah, so yeah, they have segmented mirrors because it at some point, like around 8 meters, and maybe a little bigger than that, but the logistics of just handling a single piece of glass that big and getting it transported from where it's fabricated to where you want to use it and things like that just become prohibitive. And that's where stuff like the 30-meter telescope comes in then is nobody ever figured out how to make a single piece of glass 30 meters in diameter. But
Or at least one that was that optically smooth.
yeah, right. Yeah, well, that's the thing, right? It's got to be smooth and like James Webb, right? I mean, if you were following that while they were basically booting it up, they had to phase all those segments up. And after it got on orbit and after it cooled down, then they had to go through a phasing ritual and they may have to do it from if something makes it dephase, they may have to redo it from time to time. And same with 30-meter telescope, they're going to have to phase that more often than the James Webb because the 30-meter telescope will also be subject to some unpleasant things like gravity sag and stuff like that. So,
Okay. Are you willing to share a copy of your seminar?
yeah, absolutely, yeah.
Yeah.
Should I make it how about I make it a PDF and send it to Sue?
All
And
right.
now I don't think the videos will show up in a PDF, or can I just share? Can you just share it as the whole like the Google thing? I don't know. I don't know how that
Yeah.
works.
Yeah. You can share it. Just send her a copy of the Google Slides, and we'll take it from there.
Okay,
And we've got all the links there. If we can't keep it, well, you can make it into a PDF and be able to click the links.
yeah.
So,
Well, I've already shared it with Sue, so I'll just have her get hold of me
all right.
if she needs something else. So she's probably forgotten more than I ever knew about this kind of thing.
So some anonymous attendee was wondering what you need to major in to specialize in optics.
Well, there's kind of historically been two paths. One is physics, and the other is electrical engineering. I went the electrical engineering path as an undergrad and then blazed my way into optics in grad school. So, or you could go to, some places like University of Arizona and University of Rochester have like optics departments, right? And so I'm not sure what kind of degrees they have, but I mean, it depends on what you want to work in, right? If you want to be more applied or interested in the signal processing and all that stuff, I would encourage you to major in electrical engineering. If you're way more fascinated with galaxies at the edge of the known universe, then you should be a physics major.
Yeah.
So
Okay. So
pay attention to math too, by the way. If you be good at math,
yeah.
don't let that slide. That opens the door. And in fact, you'll never wake up and say, "Man, I wish I'd spent less time studying math." It just never happens. So it's a
So,
game.
so one inquisitive viewer was wondering if you could again briefly explain how lasers clarify images from a long distance. So how do you use the lasers to clear up images from a long distance away?
Well, I didn't really touch on that. That's kind of next level stuff, but the standard way to do it. So that Hartman sensor thing I was talking about, the adaptive optics system, requires a point-like source of light to provide signal for the wavefront sensor. And so there are plenty of stars up there that work if there's one close enough and bright enough to whatever you're interested in, then a natural, these are called guide stars, by the way, then a natural guide star will work just fine. If there's not, and this is also fairly typical, is that there's just not a natural guide star close that's bright enough and close enough to your object of interest, then the next thing that's done is a laser is shined up into this. There's a layer of atomic sodium about 90 kilometers above the Earth, and you can, let's see, I think they excite that to make it fluoresce, and the light that is scattered back towards your telescope then drives the wavefront sensor. So that's the main way lasers are used for that sort of thing.
Okay. So we did have someone look up the answer to the polar mirage, and it's just a special case.
Oh, okay. All right.
So,
That's fine. I'm not, well, I'm going to look up polar mirage after we're done and see what that is. I'm not sure what that is. So,
and if I know how to drive this correctly, the answer should be in the Q&A.
okay.
So someone was wondering whether there are adaptive optics used at all in consumer level applications. So in other words, has the price come down enough for us to use it in consumer electronics?
Here, let me grab a card here. So I was actually at a conference on Maui last week, no, week before last, and I ran in to an old friend of mine, and he now is teamed up with a company called Planewave, and Planewave makes commercial telescopes, but with as L mounts, like you can buy one to put in your backyard if you want to, and then Michael Hart and this company here, I don't know if you can see this or not, Hart side, they make adaptive optics to go on those. It's expensive, right?
Yeah.
But it's not like you don't have to have a defense contract to buy it anymore, right? Like reasonably well-off retirees like Dr. Roggemann, I could afford one. Problem is, where we live, there's a lot of light pollution, so I wouldn't put it here. And then I thought, well, I could put a deer camp. Like, well, I'd have to cut down a bunch of trees at deer camp, which would then change the deer hunting, ecology. And so anyway, I'm just going to do it that. But anyway, like the low end for just a telescope and the mount and the drive electronics and all that stuff, like 26,000, and you throw another $10,000 or $15,000 worth of adaptive optics on the back and be in business. That's the consumer grade. So that's kind of the entry level. So, but like I said, that's the price of a car. Probably less than the price of a car right now. So, that's what's at. So, it's a hobby for well-off people.
Yeah. Someone was wondering if turbulence could be a cause of the reported UFOs.
Well, probably. I mean, some. I mean, not all of them. You can't leave the aliens out. No, I'm just kidding. I am certain that some of them, but I suspect that there's a multitude of, causes and so, of these. They don't even call them UFOs anymore. They call them something else. But I'm sure there's a multitude of things that have gone into that, and
okay,
it doesn't seem likely to me, by the way, if there are aliens, that they would go to all the bother to get here and not actually say hi, right? It certainly be the first thing I did. So,
well, maybe it's just that we aren't listening.
yeah, and who knows? But strange optical phenomena has got to be a fact, right? So
yes.
So
I don't know if you know this, but someone was wondering if the image of stars from Earth are affected by sunspots, corona mass ejection, solar wind, in addition to atmospheric physics.
Well, so space weather does affect the atmosphere. And so,
But does it affect the light?
well, it doesn't, I mean, the only thing it could really affect would be like the background radiation, right? Right? Because when you look through the atmosphere, right, the atmosphere is glowing, then there's galactic background and all that
Mhm.
stuff, and it might change the background slightly. And it might, like space weather might be able to affect our weather to some extent too.
Mhm.
But it wouldn't be a huge effect, mostly because we're lucky enough to have a magnetic field around our planet. I mean, look what
Yes.
happened to Mars. Look what happened to Mars. It has no magnetic field in it.
Yeah.
So,
Does that mean it's not very attractive?
yeah, no, not to us.
Magnetically, that is.
Yeah, yeah, yeah. So, okay.
Well, one person was wondering to know what the colors looked like, and was wanting me to turn my camera out the window. I wonder
Oh,
how.
absolutely. Yeah, I can. Yeah, that's close to peak colors. You know,
Yeah.
it's
So that's looking over at H&Y Marina. So
yeah. There you go, Leonard. You just shown everybody the only reason I ever even briefly considered looking for a job in the dean's office right there. It passed quickly, but if you're going to work in the dean's office, that's that's very nice, you know. So,
yeah, looking out there, I mean, it is this time of year. It's especially special.
yep,
So,
yep. So,
oh no, someone was saying they can see my house out that they could see their house when I turn my camera out the window.
oh, okay.
Oh
Yeah, I just can't see my house. You know, so, all right. Well,
no, well, I know if I turn it down the lake, and
yeah.
if we have the right temperature inversion,
Yeah, well, maybe. Yeah,
yeah,
it could form a duct over Grosse Pointe. You might be able to see it then. So,
yeah, okay.
yeah. So,
Well, that's about it for the questions.
okay. Well, like I said, if there are any of my old students out there, that feel free to drop me a note sometime and let me know how your career is going and unless you're mad at me for some reason and then you know don't bother. just know that I'm not messing anybody else up anymore. So,
All righty,
okay, thanks, Leonard. Thank you,
sure,
everybody.
thanks.
Bye now.
And one last thing, let's see. I will end with, let me share my screen with the thank you. So there
All
you
right.
go.
You're welcome. Thank you.
All right. So we'll see you next week. Bye-bye.